Here we're going to look at conservation of energy, and that's where we're really moving energy between systems and how we can use that to solve problems. And this is really the crux of why do we care about energy, is because it's conserved and it makes us be able to relate things that we wouldn't otherwise necessarily have thought could be related. So we've already talked about energy being conserved. And this just means if an energy system gains energy, it must have come from other energy systems. If an energy leaves an energy system, it must go into other energy systems. So energy can't be lost, created, destroyed. It just moves from one place to another. So if it moves from kinetic energy, it's got to go into gravitational or into thermal or into any of these other places. And so mathematically, there's two ways of looking at this. Either the total change in energy equals 0, or the total energy initially equals the total energy after. So the initial energy equals the final energy totals, or the total change in energy equals 0. And both of these forms are useful for different situations. So in example 1, a toy cannon is used to launch a ball straight up in the air. The spring inside the cannon has a spring constant of 15 newtons per meter, and it's compressed 5 centimeters when launching the ball. If the ball has a mass of 10 grams, how high can the cannon launch the ball? So when we're working through these, we want to think about what energy systems are at play here. So I'm just going to kind of sketch things out here. So originally, we're compressing a spring. So we're going to lose some spring potential energy. It's going to go down. When it's, spring potential energy is going to be where we kind of store energy initially. Then that energy is going to become kinetic energy as it launches it. But now as the ball goes up, it's going to lose kinetic energy, and that kinetic energy is going to become gravitational potential energy. When it's at the peak, all the energy that we initially had is now gravitational. And then what's going to happen is it's going to start falling back down. It's going to lose gravitational. It's going to go back into kinetic energy. And if it falls back in the cannon, it might compress the spring and go back into spring potential energy. But the point here is, initially we're thinking about all that lost spring potential energy is going to eventually end up as gravitational potential energy. Again, because when you're at the peak of your path, you're no longer moving. So that means I can just compare these two, and I can say that the change in spring potential energy plus the change in gravitational potential energy has to equal 0. So that means that spring potential energy has to equal gravitational potential energy. And this is just from moving the spring potential energy to the other side. The reason I'm putting the negative on the spring potential energy will make sense in just a second here. So spring potential energy is 1/2 K times delta x squared. And GPE change is mg delta h. So you'll notice I know everything but my delta h, which is what I want to solve for. Because the spring was initially compressed to 5 centimeters, after it launches the ball, it's no longer compressed. So we know that the final compression is 0 centimeters. So we're going to have 1/2 K times delta x final squared minus delta x initial squared divided by mg, and that's going to equal delta h. So 1/2 times 15 newtons per meter times delta x final, we said was 0, 0 meters squared. The initial and we still need a negative on here. The initial was 5 centimeters, so 0.05 meters divided by 10 grams, which is 0.01 kilograms. Yes. And G is 9.8 meters per second squared. If you run through the units, you will be able to check that we do end up with meters at the end. I'm going to really quickly plug this into a calculator here. 0.5 times 15 times, forgetting my negative, 0.05 times 0.05, 0.01 divided by, and we get about 19 centimeters. Delta x equals 0.19 meters. So you'll notice the delta, or the negative from the delta SPE, is going to cancel out with the fact that I'm doing a final compression of 0 minus the initial compression of 5. So this, the whole way that we solve these is just by looking at what are the two changes in, or what are the two or more energy system changes, and add them all up, and then set them equal to 0, solve for whatever the unknown value is. A second example here is a toy car drives off the edge of a 1.25 meter table. So delta H is going to be negative 1.25. The car has a speed of 6 meters per second right before it hits the ground. What was the initial velocity? And so this looks weird. It doesn't feel like we have enough information here initially, because we've just got how fast it's going at the end. We don't even know what direction it's going at the end. And we've got the height that it changes. But let's just think about it. We start with, as it falls, it's going to lose gravitational potential energy, and it's going to gain kinetic energy. And right before it's the ground, it just gained a bunch of kinetic energy. There's nothing stretching or compressing, so I don't have to worry about spring potential energy. There's no work being done on this system. So we can just go like this. We know the change in gravitational potential energy has to equal the change in kinetic energy. So negative GPE has to equal change in KE. The negative GPE is going to be negative mg delta H. The negative KE is going to, or the delta KE is going to be 1/2 m times delta V squared. You'll notice here, this is why we don't need the mass actually, because there's a mass on both sides, so I can cancel that. And I'm getting negative 2g delta H equals V squared minus V initial squared. And if I'm trying to solve for V initial squared, I'm going to add the V squared over. So V squared minus 2g delta H equals, let's flip those, V naught squared. So if I move the V squared, so that should be a plus. Yeah, I flipped some negatives too quickly in my head. So V naught squared moves over, 2g delta H moves over, everything becomes positive. Then we're going to square root it. So we're going to get plus or minus V squared plus 2g delta H equals V naught. And in this case, we know that that just means, because it's which direction, we're going to stick with just the positive value, because we actually just care about how fast. So this means that V naught is equal to the square root of the initial speed of, the final speed of 6 meters per second squared plus 2 times 9.8 meters per second squared times delta H, which is going to be negative 1.25 meters. If we plug all this in, we get 1.25 times 9.8 times 2, 24.5, 36. Is 11.5 square root of 11.5 is 3.44. And we expect meters per second. Let's just double check that real quick. This is going to be meters per second squared, meters squared per second squared. Our second term is going to be meters per second squared times meters, which also gives us meters squared second squared. So when I square root it, I'm left with just meters per second. So that's how conservation of energy is used. If we add energy, or if work was done on the system, then instead of equaling 0, we just have it equaling how much energy was added or removed.